This is the video lesson for Newton's first law and constant velocity. The learning target for this lesson is, I am learning to describe the conditions under which a system's velocity remains constant. The success criteria for this lesson are, I can understand that the net force on a system is the sum of the force vectors being exerted on that system. I can understand that an object is in translational equilibrium when the net forces acting on an object are zero. I can understand that when the net forces acting on an object are zero, the object's velocity will be constant. And I can understand that the net forces on an object can be zero in one direction, but be non-zero in another direction. Alright, so let's talk about Newton's first law and net force. So you can see in the diagram, or in the picture to the left, there is a skydiver falling under his parachute, or coming down under his parachute, and there is a free body diagram with a balanced force. So we have the force of drag up and the force of gravity down. So net force is the vector sum of all the forces acting on a system. So we have a sum here. We have the F net is equal to force 1 plus force 2 plus force 3 all the way to plus force n. So the net force determines the system's overall acceleration. The net force can be calculated in each direction independently. So we can talk about the net force in x or the net force in y. So let's talk for a second about translational equilibrium. So translational equilibrium occurs when the net force on an object is zero. So F net equals 0. So in this state, the object experiences no acceleration. So we're talking about a situation where an object is at rest or it is moving at a constant speed. So we have a derived equation, what we're talking about when we have a translational equilibrium. So this is the sum of forces are equal to 0. So we have an index here of I, and the forces are sub I. So however many forces we have all total, so let's say we have I is equal to 3, so we would have force 1 plus force 2 plus force 3. So that's the sum of forces all together, and those would always equal 0 when we're in equilibrium. So for some examples, a soccer ball sitting in the grass, it is at translational equilibrium because the sum of forces are equal to 0. Another example of translational equilibrium would be a car driving on a straight level road at a constant speed. So the forces equal out on the car, so it would be in translational equilibrium. So let's talk about constant velocity and zero net force. So when net forces are 0, an object's velocity remains constant. Constant velocity means that there's no change in speed and there's no change in direction, because remember that that velocity is a vector. So this is a direct application of Newton's first law, which states that an object at rest will stay at rest, and an object in motion will stay in motion unless acted upon by a net force that is outside of the object. So net forces can be in different directions. So net forces can be 0 in one direction but non-zero in another. So F net x can be 0, F net y can be a non-zero. So for an example of this, we can think about an elevator accelerating as it moves up. So we're talking about an elevator that is accelerating rather than moving at a constant speed. So the forces in the x direction are 0 on the elevator, so it's not accelerating in side-to-side motion. But the net forces in the y direction are non-zero, meaning that it is accelerating in the y direction. All right, let's look at example number 1. So 3 forces act on an object. If the object is in translational equilibrium, so it's in equilibrium, which of the following must be true? 1, the vector sum of the 3 forces must be equal 0. 2, the magnitudes of the 3 forces must be equal. 3, all 3 forces must be parallel. So if it's in translational equilibrium, the vector sum of the 3 forces must equal 0. So that is definitely true. So the magnitudes of the 3 forces must be 0, and all 3 forces must be parallel. So these are not necessarily true. for it to be in translational equilibrium, but the vector sum of the forces has to be equal 0. So the answer to this question is number 1 only, so A. Okay, example number 2. A skydiver is falling through the air attached to a parachute. The mass of the skydiver parachute system is m. The upward force of the air resistance exerted on the system is given by the equation F sub air is equal to AV squared, where A is a constant that depends on the shape of the parachute, and V is the speed of the system. After falling for a short time, the system reaches a constant speed V sub t, which of the following is a correct expression for V sub t. Okay, so we know we have a constant speed. So a constant speed is V sub t. So that means our forces must be balanced. So we have, so let's draw a free body diagram here. So we have the force of gravity pulling down, and then we have the air resistance pushing up, and these two forces must be balanced to make the parachute the person doing the skydiving fall at a constant speed. So if we look at our sum of forces, so sum of forces in the y direction, we have our air resistance minus our gravitational force is equal to 0. So we can say that the air resistance is equal to our force of gravity. So our air resistance then is equal to AV squared, and that's equal to m times g. The gravitational force is always m times g. So V squared, so V is Vt, that's the speed at the point that these forces are equal to each other. So we have A times Vt, and that's squared, is equal to mg. And we're solving for Vt. So if we move this up here, so I'm going to divide both sides by A. So we have Vt squared is equal to mg over A. So then Vt is equal to the square root of mg over A. So we have square root of mg over A is answer choice number C. Okay, so this is example number 3. When an object of weight W is suspended from the center of a massless string, as shown at left, the tension of at any point in the string is, and we've got these answer choices. Okay, so we have this string, it's attached at these 2 points, and there's a mass hung on it, and the mass is W. So just a quick reminder that the force of gravity is m times g, and we call that also W. So the weight of an object is also considered the force of gravity, and that is calculated by multiplying the mass of the object times g. Okay, so we've got this string here, and we can think of this as being the force of tension on it. These two forces are equivalent to each other because it's the same string. So we need to break up this force into its components. So really all we care about is the y component. So if we have this is our angle theta here. So if we look at this being our force of tension in the y direction. So let me draw this somewhere else here. Okay, so this is our force of tension. This is our angle theta. And this is our force of tension in the y direction. So force of tension in the y direction is going to be equal to our force of tension times our cosine of theta, because this is the adjacent side of this triangle. All right, this is the adjacent side. Okay. So let's draw a free body diagram of what we have so far. So we have facing downward is the force of gravity, or weight, and upwards we have the tension force in Y. Okay, so we want to do our sum of forces here. So we have the sum of forces in Y is equal to, now really this is 2 times the force of tension, because there's two of these diagonal forces, tension forces, and they both break up into the tension force in Y. So each of these forces breaks up into one of these Y components. So we have 2 times the force of tension in the Y direction minus our weight. And those together equal 0, because the situation, the whole thing here is at equilibrium. The mass is not accelerating, so everything is in equilibrium. So we have 2 times Fty equals the weight. So Fty we know is Ft times cosine theta, so we can replace that. So we have 2 times Ft cosine theta is equal to W. Now we're solving for Ft, so I'm going to divide both sides by 2 times cosine theta. So we have Ft is equal to is equal to W divided by 2 cosine theta. So our answer choice then is W over 2 cosine theta, which is answer choice C. Okay, so what have we learned in this video? We learned about the net force. So net force on an object is the sum of the forces acting on that object. We've learned about translational equilibrium. So an object is in translational equilibrium when the net force acting on the object is 0. And we've learned that the net force can be different in different directions. So the net force in the x direction and the y direction can be different. All right, thanks everybody.